Alright, hello everyone. Welcome to Lab 5. This is the intro video for the, Lab 5 lead and lag compensator design. Before you start the lab, you should at least read over the notes for the lead and lag compensation design, as you're going to have to do the design procedures as you learn in class for the design techniques in the actual procedures. Moreover, you should review the Nyquist plot and understand what the Nyquist plot is. You don't need to know how to draw one for this lab, but you will need to know how to interpret a Nyquist plot. So just bear that in mind before you start this lab, that those are tools that you'll have to know before actually doing the lab. Otherwise, you will get confused, very likely. Okay? So what I want to talk about in this video is going to be slightly longer than the other ones because there's quite a few parts of this lab, and this is actually the biggest lab in both in terms of your grades that you get assigned, as well as the actual amount of marks that is in this lab. However, a lot of the marks are assigned to the actual procedures themselves. So the lab report isn't worth a whole lot compared to previous labs. Okay. The lab for the application for this lab is the same as the previous labs, Lab 4. In Lab 4, you worked with this sort of UAV model that's trying to follow a line. We're going to do the same thing in this lab, so it's the same model almost. The only difference is that we're going to introduce delays in the system. Now, you may learn in class, or as you'll read in this lab manual, an otherwise stable control system, right, with a controller that stabilizes the plant, can be rendered unstable if you introduce a delay in the system. A delay being that, of course, if you are making a measurement, there might be some time it takes for that signal to be observed by your control system, think computational delay, or even a delay to actually actuate the control action onto the plant, right? There might be a communication delay, for example. This lab is how do we deal with this sort of communication delay? And you're going to use the lead and lag compensator design to deal with the introduction of this delay and make your system essentially stable even when a delay is inserted into the actual model. Okay, so that's the high level idea behind this lab. The lab is structured into a number of procedures. Each of these procedures is going to use one MATLAB script, pretty much, and they're all cited within the procedure. So if I go to MATLAB right now, your files that you will have access to, you'll see there's going to be a procedure 5.1 simulate, procedure 5.1.m, procedure 5.2, procedure 5.3.m, procedure 5.4 simulate, procedure 5.5 simulate. Okay, and these are all associated with the respective procedure numbers in the lab manual. The lab manual will tell you to open one of these files, edit them, and in particular, the ones without the simulate, you'll be editing. Procedure 5.1, you'll pick a gain. You can see here it says pick an appropriate gain k, and you're going to set this variable k. In procedure 5.2 and 5.3, you'll actually design the lead and lag compensator, and you will actually set alpha and t, which, if you look in the lab manual, correspond to the parameters of the lead and lag compensation. Okay. The one thing I want to point out is, although this lab can be done sort of in parallel, you can do the lead and lag compensator design in parallel, there is a dependency. So if I show you this dependency plot that I keep in the lab manual, you'll see that deliverable 5.1 up to 5.3, which is essentially the first procedure, procedure 5.1, that procedure is relied upon by the lag compensation design and the lead compensation design. And then finally, the last deliverables depend on both being implemented. So if you're splitting up work, make sure to propagate your changes to those files to your partner in case they are working on a ladder dependency. Okay. So you change these numbers in these files. When you change the numbers in the files, you should always run it. I believe the lab manual tells you to do so, but you should always save the file and run the script. Okay, and then you can open the model in question that uses that script, and usually the lab manual will specify which model to work with. But for the first couple parts, including the lead and lag design, except for the last part, you're going to be working with the Lab 5 model system. So that's here. The model system has our drone model from Lab 4. You can see here a lead and lag controller, and you can see the alpha and T's are already placed there for you, and that's why you only have to edit the MATLAB script. You don't have to actually edit the Simulink diagram. There's a gain here, which you will set in procedure 5.1. And the input and output perturbations are already set. So when you use the model linearizer, you're going to get the open loop responses, okay? Not the closed loop responses, the open loop responses to the system, to inputs. So in particular, you might want the open loop Bode plot or the open loop Nyquist plot, for example. Yeah. So the one thing that I want you to pay attention to with regards to this model is you'll see over here, there is something that you haven't seen before, and there's this switch and a delay. Now in the lab manual, zoom in here, in the lab manual it tells you to switch this delay switch at certain times. And it will say, make it so it follows the path with the delay or without the delay. And what this means is, if you look at the switch, you can see that on one side the path is connected and the other side the path is unconnected. And so here, in this case, Y, the output, is being fed through this path from the drone model. And it's not passing through a delay, which means it's undelayed. When I double click this, now Y is being passed through the delay block. And so it's actually, there's a delay being introduced into the system. So the idea is that when you have the switch selected to delay, it's now the system that you're going to simulate or get responses to, a Nyquist plot or a Bode plot, is going to correspond to the system that has the actual delay in it. Of course, if you design your system poorly, you might have a stable system when closed loop, when this path is going without the delay. But when you add the delay in and save the model, and you run the model linearizer tool, you might have it be unstable. So I'm just going to quickly show that as part of showing the last plot, the few things that we are going to do with the model linearizer. So let me just switch it to that and save. And I'm going to put an artificial gain here. 400 is fine. This is okay. And I'll do 500. It's not actually allowed in the lab manual, but I'm going to use it anyways. So I'm going to run that. Procedure 5.1. It's executed. Perfect. I'm going to open the model linearizer tool. Apps, model linearizer. There it is. I clicked it twice. Oh, that's no good. Perfect. So it is up now. So what I can do is, you've already seen how to acquire a Bode plot, but let's acquire the Bode plot, shall we? So I'm going to click the Bode plot here. It's already set up with the input-output perturbation, so that should be fine. It's going to do our simulation here. Hopefully everything is a-okay. Perfect. It's now going to render our. It's going to now render our Bode plot here. All right. So here's our Bode plot. It's looking good. One feature that I wanted to point out in this Bode plot is if you right-click and you click characteristics and you go all stability margins, you will get the gain margin and phase margin. If there is a gain margin, you'll get a gain margin. If there's a phase margin, you'll get the phase margin, which you'll need for your lead and lag compensator design. As you know, if you reviewed your notes, it'll draw the gain crossover line. It'll also draw the phase crossover line, but you won't cross that probably. And then you can see at the gain crossover, there's a little point added here for the phase margin. And if I hover over that, you can see it says I have a phase margin. A phase margin I got is 5 degrees. That's not a very good phase margin. But it's also telling me I'm closed loop stable, which is great, right? So what happens if I add a delay, right? So let me double click this and save the model. And you will see that the Bode plot changes quite a bit. Of course, with a delay, you will have some unusual behavior, and you may remember from an assignment that the Bode plot with a delay looks quite different. Let's just add that in, see what happens. And you can see it's very different. And of course, if we were to click all stability margins, you will see pretty much right away that's something, it's not quite closed loop stable. And you can see right there, it says, no, it's not closed loop stable. The other plot that you will collect is the Nyquist plot. So here you might either find it here or you might find it by clicking the arrow. So I'm going to click the arrow here and you'll see Nyquist over there. If I click the Nyquist plot, I'll also be able to, of course, check stability that way. And that's actually the most reliable way of doing it. And we obviously don't want, because P of S is stable, we do not want encirclements of the critical point, -1. So if we zoom in on that, you'll see right away there's an encirclement, so I'm clearly unstable. We will expect you to explain your answer, of course, in your lab report. So that's pretty much all there is to do in terms of the model linearizer. You're going to acquire Nyquist plots, you're going to acquire Bode plots, you're going to switch between delayed and undelayed and saving the model system file. And then you're going to use all that information to help guide your design for lead lag design in the later procedures. And of course, you can always go back and change your answers, but you should expect that you'll be able to do it pretty much on the first try. You'll find that it works out. So I'm going to close the model. Yeah, I'm going to close the model linearizer. So that's all there is to do in terms of the model system file. Another comment that I want to make, procedure 5.2 is straightforward, but procedure 5.3, which is actually the lead design, you will learn in class that you might have to adjust the DC gain of this the lead controller. If you want to do that, I've left a line of code here. You could take the previous DC gain that's applied to the lead compensator and change it to be whatever you want here. So that's if you need to change the DC gain, of course. All right, and that's of course to meet the 1% steady state spec, if possible. Finally, you will at the end of the lab, you will run procedure 5.4 and procedure 5.5 simulate. These actually run the real system Simulink diagram. Now the real system Simulink diagram, you don't need to open, you don't need to change anything there. It already has the delays inbuilt. I'm going to open it to show you what it actually looks like. So let's just open that up. What you'll see is you'll see your lead lag compensator with a gain, just like before. But what you'll see on the right hand side is a little change. There's a drone model, but before and after the drone model is a send and receive message block. And what these blocks do is they're sort of simulating the idea of communicating with some sort of remote drone and simulating the delay that's introduced by that. So there's some delay in sending a control action to the drone, and there's a delay receiving observations from the drone. And as you can view these as communications delay over a long distance. And so this is actually modeled in the model system by just an artificial delay block. But here we're actually essentially incorporating that as part of as a simulation of this sort of delay that's happening through a message style delay. You will learn if you ever take an elective that this is not quite a perfect model. Really, you'd want to simulate a discrete time system to model these kinds of effects. But it turns out delays, even in a continuous time system, can actually cause problems, and we can solve at least some of those problems with this lead lag compensator design. So that's all you need to know about this modify. You don't even have to open it. So I'm going to close that. If you run the procedure 5.4 or 5.5 simulate, you'll get a simulation of your closed loop system. In my case, the system we know with the delay was unstable. So if I run this right now, I'll run 5.4. We should expect bad results. So let's just see what happens, right? This might take some time. Oh, there you go. Bad results. And you can see, oh, wow, that definitely is not stable, right? So there's our UAV in the world plot. And you can see that, well, it stopped, actually. And that's basically the emergency stop. If you're unstable, there's a special emergency stop in the actual simulation block, the simulation diagram, that just decides to give up and says, no way, you're not running your controller on this. And you can see clearly the error is increasing, right? It's clearly unstable. If I were to maybe change some gains here, so if I made the gain really small, which you can't do actually for this lab because you'll need to meet a specification, the closed loop system will probably be stable, but it's probably not what you want. And you're going to use the lead lag compensator design to actually both achieve the steady state spec as well as getting stability. So let's run this. I suspect this will be stable, although it will probably not be an ideal convergence. Well, that's a good sign. It's taking a long time. There we go. And there it is. There it is. It converged. It's definitely not meeting the steady state specifications. It's quite far away from the actual reference that we are trying to track, but it's at least, and you can see the error there. That's quite a bit of error. That's like 9 or 8 error from our reference here, but it's at least stable, right? So your job is going to be, can you make it so that gain is large so that you have basically 0 error for all practical purposes? It's not going to be 0, but close to 0. While still guaranteeing this sort of stability, okay? So that is all there is in terms of the actual procedures, the files, and how to run things, what numbers to change, and so on. In terms of the lab manual, there's a few things I want to point out. The first thing I want to point out is in the lab manual, there's a point where you're going to work with the frequency on the Bode plot on the x-axis. And that is when specifying the specifications for the lead and lag compensators. You'll see over here, I say something like, let omega GC determine 0 dB crossover frequency in rads. This is really important, okay? Do not use hertz. You'll probably get a really wrong answer and it might just not work, okay? So make sure the units of your omega GC when you're using these formulas are always in rads, okay? So that's the first thing. So I said here rads. What I actually mean is radians per second, right? So the frequency of these signals, or the x-axis when we call frequency, instead of hertz or 1/seconds, you should be using the units radians per second. The final result is you're going to multiply by some number, which is 6/100, which is a unit of time. It's basically in seconds. 6/100 is in seconds is 60 milliseconds or so. And so when you multiply those two numbers, you're going to get just radians. And that's actually your phase margin specification in radians, right? So if you need it in degrees for some reason, bear in mind that you still got an angle in radians. And your original frequency starting point was in radians per second. Okay, so just that's what I want to clarify, what I was trying to say here. All right, we can continue. And of course, you'll see that throughout. I may not always say it to be in rads, but it should be always in rads, okay? In radians, I should say. Scrolling through, the last thing I want to point out is the actual grading scheme. So you'll notice, so in past labs, the reports in the lab experimental portion have been sort of 50-50 or close to it. This time it's very heavily weighted towards the experimental part. And that's because the procedures themselves take way more time this time around. You have to actually use the design equations for the lead and lag compensators to get your answers. That makes sense. So that's both a good and bad thing. Of course, it's good because once you're done the procedure part of the lab, you've gotten most of the marks. In particular, you can see here 36 out of the 57 are the actual practical part of the lab, and that's about 63% of your grade. And you'll find that about half the report questions are fairly straightforward, so you should be able to get a pretty good mark on this lab very easily. It's just a lot of work. But remember that although it's a lot of work, it is good practice for your exam because you'll have to actually design the leading lag compensator here using a Bode plot that you acquire by the simulator, of course, the model linearizer. So just bear that in mind. And besides that, I believe that's it. That's it. Good luck on your labs, and hope this term has gone well. And I'll see you on Piazza.